Give me a second.
What, yes, sir?
Go ahead.
Okay. So I've basically adapted this from two sources. I didn't actually put them in here because I forgot, but I'm going to send them to you in an email. There's a nice set of lecture notes by this guy called Castro. He's, I think, in the University of Amsterdam. And then there is Vapnik's book, which is pretty nice, but I wouldn't advise, I mean, I've done it and it was hell, but I wouldn't advise reading Vapnik's book on its own. I'd advise probably reading the notes that this guy produced, which I've mostly adapted this from, to be honest, although I've edited it because there's some mistakes in it and I'm not quite sure that I like some of the notation. So anyway, I'm going to give you a quick introduction. And I said originally that I wanted to get as far as the Rademacher complexity, which is basically just a way of computing some kind of complexity measure for a space of hypothesis.
James, that is, we are not seeing your slide, we are seeing the flasks stuff.
Yeah, that's what we are saying. Yeah.
Sorry.
Which is equally like cool, but.
Whoop. Let me try again. Yeah, I'm only in the title slide. I know, so it doesn't really matter yet. You see that?
Yeah.
Okay. Okay. So yeah, I'm not going to go as far as Rademacher complexity because I'm not so new to this, but at the same time, when I was reading back over this, I realized I've forgotten a lot of it, and you're probably going to have questions that I'm not even going to be able to answer. So we're going to go as far as something that's easier to understand, even though it's not quite simple either. And maybe in its follow-up, we'll move on to things like divisive dimension and Rademacher complexity. I think to have an intuition for this is all we need for the moment. I'm not going to go through any proofs either because we'll be here all day. So let's see how this works. Page down. Yeah. So the first chapter of Vapnik is quite nice, and he goes through basically the four ideas you have, which constitute statistical learning theory, and they're not all useful for us. I think two of them I don't think we will need for what we're going to be interested in. So I've reduced it to two. So these are, what are the conditions for consistency of learning process? So what makes a learning algorithm consistent? What makes it reliable? So you can think about this. I know I've worked with plenty of computer vision algorithms where you have some kind of, not computer vision algorithms, computer vision and neural network architectures where training now and training in 20 minutes produces completely different results, and they may not be even convergent results. So you have very, very breakable models in computer vision a lot of the time, and that's not a consistent learning process when you train with those, because you might end up with a model that converges to a really nice solution, or you might end up with a piece of shit. The second of those is pretty obviously a thing of interest, which is once we have one of those algorithms which we know is consistent, how can we control how well it generalizes? So yeah, sure, it can be consistent and learn to do things, but if it doesn't learn to do something we don't want it to do, we know that we want it to do, then it's not particularly useful for us. So consistency of learning and controlling generalization, they're the two things that are of interest to us. And for this, I'm just going to talk about, for this, I guess, session, I'm going to talk only about the consistency part. So yeah, if we can derive a theory that tells us about both of these two things, then that's pretty much all we need to understand how well, first of all, a learning algorithm and a hypothesis space is for solving our problem. And if we can understand that well, then we can say some things about it rigorously. For example, we can say things very rigorously about support vector machines because they were derived from this kind of theory. But we can't say things as rigorously about convolutional neural networks because, well, quite frankly, there is no learning theory really developed well enough to understand it. So first of all, I'm going to go through some nice, easy stuff. So this should be somewhat fun. And then towards the end, we're going to get to the point where these equations will start to be annoying. So yeah, I'll start with stuff we all know. So in order to do this, we need to actually define what learning is, which is fair enough. If you want to study something rigorously, then you have to have a rigorous definition for it. And from Vapnik's perspective, learning theory only really applies to supervised learning, which I guess makes sense. And I know there have been some attempts to expand this to reinforcement learning, but I haven't really read about them. Maybe we can do that in the future. But for now, I'm just going to talk about supervised learning. And I'll keep talking, or I'll keep mentioning later on about the restrictions we make about what we're studying, just to make it clear that we're, for the moment, talking about a very small subset of learning theory, or the possible learning theories. So the first of these is just a data set. I'm not going to read it out. It's pretty obvious what I'm talking about. It's just a rigorous definition that says we have some samples drawn from some distribution. Maybe we know it, maybe we don't. And if we have a finite number of them, we may have n, and we can just denote that by curly d, n, and we call that a data set. Cool. Of course, if you want to do learning as well, not only do you need a data set, but you need to do something with it. You need to quantify how bad your model is. So you're going to need some kind of loss function, which just is a mapping of your label space or your target space, or a mapping of Cartesian product of those spaces to some real valued scalar, which tells you good or bad, effectively. Okay, we know that already. That's pretty obvious. So this is Vapnik's notation for a hypothesis set, and I like it a little bit more than the Castro ones, even though I draw more, so a lot more so on the Castro notes. So he says a function set f, which is curly f, is any set of functions f of some function, f of some argument and some set of parameters, and that parameters is a set of some larger, or from some larger set, which we define on our own, and we define that in a way that makes it convenient later on. It is called a hypothesis set, that function set, if it maps our inputs to our outputs. Okay, that's pretty obvious. And the space of parameters can be any size, really. It's an element of some real valued set, typically. And that comprises our hypothesis space. Now, in the sense of a convolutional neural network, again, I'm going to talk about those as my example because we all know them. Your hypothesis set is not the manifold of all the possible functions that your not the manifold of all possible functions that can be realized by the structure of your convolutional neural network. So let's take, does everybody know what a unit architecture is? Just nod, you don't have to say yes.
Yes.
Yeah, okay. So just to explain what that, so a unit architecture, for example, you can have so many parameters, they're all encoded in your convolutional layers. And let's say, I don't know, we have 100,000 parameters in that model. A hypothesis set is the set of all possible parameterizations that we can have, not all the possible parameterizations of that kind. So for example, since on a computer we're restricted to floating point numbers, that set isn't actually infinite, even though in theory it is infinite. So when I talk about a hypothesis set, I mean typically some kind of finite hypothesis set that is not actually the set of all functions that can be represented like that. That gets more important later on when we talk about trying to define simpler measures of complexity. But just think about a hypothesis set as, for the moment, mostly a finite set of functions, not infinite, like that might suggest. Okay. So we go back. We have our data, we have our loss, we have a function set. So we have a function that can do something with our data, a loss that can tell us how good our function is at doing something with that data. But we also want to define something called statistical risk. So statistical risk is kind of like the expected loss. It's a little bit more nuanced, but it's effectively the same thing. It's just a fancy name for the expected loss. It is the expectation of our loss function over the distribution of our data. Now, as I said, and as you know, because we talked about this last week as well, we don't know the distribution of that data most of the time. But in theory, at least, you can compute your statistical risk, which is a measure of how good your function is that you've chosen from your hypothesis set. You can measure its risk by taking an integral over the probability distribution P, and that can tell you effectively how good or bad your model is. That is your risk. And this is the most important object that we're going to be talking about today, the risk function. Okay. So given some risk function, that's what allows us to identify not only a good model, but a set of models that's consistent. So typically when we're training, we look at the loss function and we say, we know that this model is good because it achieves the lowest loss. Something like that. It's, again, more nuanced than that, but that's pretty much the idea of what we're doing. We're interested in consistency, as we said at the beginning, which means something more than that. It means, given a random realization of our data, we want to have always some kind of consistent risk. So we always want to have an expected low risk. So maybe we train 100 times. Our model is good if our risk always ends up being a relatively low number. So think about your risk as a random variable. So given some risk, there's going to be some function, which is, I guess, the optimal function, the one that achieves the lowest risk. And there might actually not just be one, there might be several, especially if we have a really complicated space of hypotheses. So that's just a fancy way, again, of saying that there is some function here, which is the one that we're looking for, which achieves the minimal risk. So that's the optimal function. It's the one we do the gradient descent search for most of the time. And the optimal risk, I think you can, I'm just going to do it by waving my mouse. The optimal risk is just denoted by R star. So I'm going to use that to denote from now on optimal or minimal objects. So there's possibly a set of functions that are optimal that all achieve the same risk. And if we want to choose any of them, it doesn't really matter which one we choose. It might matter if we start evaluating our test and training sets later on, but we can worry about that later. So now we have all these objects, so we can actually define what learning is exactly. So as I said, we don't actually know P of X and Y. It doesn't not necessarily even have to have analytical form, which is one of the common problems we have, even though we can approximate it analytically. If we did know it, we can compute all these things really easily, but we don't know. So in practice, we have dn, not d infinity. So we have to find some model f hat of n. So I use hat to say this is something that is obtained by using our data. So whenever you see the hat there, which is a little, that's what, I don't know, you might use different actually, you might use a different word for that, but I call this object here on top of the f the hat. We want to find some f hat trained over our n samples in some way that minimizes our risk. Okay, that's all, again, familiar, all pretty easy. So this is the learning problem. Concrete definition for it, not too unfamiliar. Basically, the function that's best is the one that's trained over the data and achieves the minimal risk, which is the minimal expectation of loss. Okay, cool. Okay, we're 5 slides down, that's good. Okay, so before I go on, it's kind of important to, I didn't do this for nothing, this is what I'm trying to say. It's important to understand that this is how the learning process is defined, because everything else will depend on it later on. And having this rigorous definition is kind of more important for the stuff I'm not going to talk about today than it is for the stuff that I am going to talk about today. So when we continue this some other time, it might be just useful before we continue in a separate session to read over this definition again and understand it. It's going to get confusing as well, because you'll see that down here, I have taken the infimum over this set of functions. And you have an f hat here. That's okay. That's the f that's trained using a finite set of data that we have access to. But you'll also eventually start to see r hats and r hats of f hats, which means that not only is this f hat trained over our finite data that we have available, but this r, which is our risk, is evaluated over that data too, which makes sense. We can't actually compute r in practice most of the time, because only can we do that if we know the probability distribution of our data. So just bear in mind that understanding exactly what this notation means is important, because things get a little bit hairy later on. Okay.
Sorry,
so like I said, yep.
Like you mean like the f hat of n would be like we would be having the minimal risk on the on subset of the DN, yeah, on subset of the data set. That doesn't make sense to measure it on the whole data set it was trained on, yeah.
Yes, I'm going to talk about that a little bit later. But for the purposes of this, let's just pretend that we're training on the whole data set. I know that's not what you actually do in practice, and it's covered a little bit later. But it's effectively the same thing, and it makes the notation easier to say we're training over everything, if you know what I mean. But yeah, we do cover that. I'm going to say that we are supposed to train on our training set and test on our test set, but I'll continue using this notation anyway, because nothing really changes mathematically. But if we do start to add in extra sets, it becomes really, really difficult to follow. So I'll try not to do that. It's already hard enough. Okay. So yeah, we defined what learning actually is, which takes longer than you'd expect. So now we can actually say what makes a learning algorithm consistent. Okay. As you might guess, it's something to do with the risk. So it's something to do with the expected risk. And as you might guess as well, we can typically say that a learning process is consistent if, in general, the expected risk of the data trained over the function that we trained or selected over the finite data that we have consistently has a low risk. Okay, I think I said that right. So, and a little bit more rigorously, we have to define what that actually means. Okay. So, like I said, we're not actually really concerned with the result of training over a single process. So training over, doing one single training run is the concern of a practitioner. When we're designing learning algorithms, at least in theory, it would be nice to be able to understand how they work concretely. So this is the biggest problem that a lot of people have with deep learning, is that they cannot do this line here at the bottom. You cannot compute how accurate, not even necessarily how accurate, but how reliable these models are. And if you can't compute how reliable they are, then this whole field of explainability comes into the picture, because, well, if you don't know what's going on, then you sure as hell have to do something about it to know what you're going to do when something doesn't go right. So rather than computing just the risk, which is, or again, f of n, or f hat of n, we want to compute the expected risk. So that is an expectation of the data that we've trained, or the function that we've trained using our data, over the data that we have available. So like Yasser said, it's a little bit more nuanced than just training on all of our data and then evaluating over all of our data, but it's pretty much that.
Yeah, just the one thing, like it says like random realization of data sets. So what do you mean? Like it's like the same data, you are shuffling it, or like something like that, or it's
yeah, so in practice, yes, pretty much cross-validation, that kind of thing. In theory, it would be nice if we could draw data sets randomly. So say we have a data set of 15,000 images, it would be nice if we could find whatever that distribution is and draw 1,000 different ones of 15,000 images as well and evaluate over that. But since we can't, we're stuck with what we have. And in practice, we have to estimate it. But
so this expectation with respect to DN is basically some sort of cross validation. You every time you are having a different validation or test set, so that makes you have a different DN for the same given DN, some sort of.
yeah.
Okay.
It could be cross-validation. It could be something else. But,
Yeah. But it's the same. It's the same set DN.
Yeah, pretty much.
Yeah.
Okay. Yeah. Yeah. Sorry, I'll try and read the text actually, because I'm thinking of skipping over things. Yeah, you got that. Okay. So this is I guess the highlight of the day. You guys, again, are going to be more familiar with this than I am, but now there's a specific type of augmentation called mix-up, which I didn't hear about until Kevin told me about it. Or told us about it. I guess he actually gave us a kind of a presentation about it, or about something else, and it came up. And in that paper, they talk about empirical risk minimization, but they talk about augmenting it as well. And I wouldn't have known what that was unless I'd actually happened to read these notes about 2 years ago. So this idea of posing learning like this isn't just for fun, and it isn't something that people do because they want to be pedantic about anything. It actually is important. So in Mix-Up, they say that this empirical risk minimization process, which is actually pretty much just what I said earlier about the process of learning, it's just a slightly more formal way of writing that in practice. So when I defined learning earlier, I kind of pretended that we had access to an infinite data set and that we knew what the distribution, we possibly could have known what the distribution is. But when we're talking about empirical risk minimization, it's the formalization of the learning process when we don't know all the data and we just have a finite amount of it. So what we kind of do on a day-to-day basis. This crops up everywhere. So if anything you take from what I've been saying today is that you remember what this is, it's going to help you, I guess, at least. And it's old as well. This was done in deepest Siberia in some lab nearly 70 years ago now. So, no, is it 70? 50 years ago. I'm bad at math. No. Yeah, it was 60. Yeah. So this will crop up everywhere. I've seen it even in the papers that don't talk about machine learning. They don't understand what this is, but we will hopefully by the time this is over. So if I can move this here a bit. So we have our data set. This time it's finite. We've drawn it from some distribution. Maybe we don't know it. We're going to assume we don't. It's some collection of training data. Our empirical risk is just the average of our training losses, okay, over a specific function. So say we have some function f. The empirical risk is just the average loss. Okay, not too hard. but just good to know what that is. Okay. So the process of empirical risk minimization pretty much comes to minimizing this object. So we want to find some f such that r hat, which is the risk. Now this is the expected risk, sorry, empirical risk, sorry. I'm going to be very careful about what I say because this is going to become harder later on when I talk about like 5 different risks. This object is the empirical risk, so it's risk evaluated on the data that we have. Given some function that we're currently looking at, f, we have to compute it by computing the average of the loss, whatever loss measure we have. It doesn't really matter what loss measure that is, of our function f given our samples. So we want to find some f that minimizes this object. Okay, that's easy. And that's pretty much the formalization of the empirical risk minimization principle there. So we want to find some optimal f hat n, so fn hat star, that is the function f from our hypothesis set that minimizes this empirical risk. So this is where the notation starts to get a bit annoying because now we have hats on everything and stars going everywhere. But again, f hat just means, f hat of n just means it's a function we've selected using our data set of n samples. The star means it's the best one we could possibly select. The r hat means it's the risk evaluation of our data set. So it's no longer the true risk, but the empirical risk. The true risk is what we would be able to compute if we knew the generating distribution of our data. And again, f is just a function that we're selecting. Although I fucked this up, these two should be the same. It doesn't really matter which one, but these two should be the same object. I'll fix that later on. So, okay. So I'm going to quickly run through everything that we have defined so far, even though most of it is obvious. So again, anything with a hat over it means that it's usually estimated using that finite data set, and anything with a star in it usually means it's optimal. Well, it will mean it's optimal. I'm not going to stray from that notation. So first we have our data set, easy. Next we have our hypothesis set. So again, our hypothesis set is just some set of functions, f. So these functions typically have a predefined structure, for example, a convolutional neural network. And we have some set of parameters that we can put with it. So this is some set of parameters that can go in as our weights, and that set can be finite because maybe we're restricted by our floating point numbers. Maybe it's restricted because we only want to work with a finite data or a finite set of parameters because maybe, I don't know, we want to reduce the work of searching through all of the possible sets of parameters that we could be using. And those two objects combined give us our hypothesis space. Okay, so our risk is pretty much just our expected loss. So the risk is just the expectation over the loss of over our loss given some function that we found which has some parameters alpha between what we predict and what we actually have. We have the minimal loss, which gives us, or which is given to us by the function that minimizes the expected loss, or well, just sorry, that minimizes the risk. So there is some f that minimizes the risk, and we call that f the one that we're looking for. The empirical risk is something that is hopefully close to this. We'll talk about this in a minute. So this is what we compute if we know everything. Maybe we don't. We probably don't. So if we can't compute this, we can estimate it using our data. So this is why the hat is here. So given some function f, we can estimate its risk using our data set. So this is what this sum is for here. And what we're looking for, again, is some f we've found using our data set that minimizes this risk. If we find that, then surely it's a good function and surely we've learned something. Okay, so that's just a summary of everything we have up to that point. And I'll do another summary in the middle before I kind of summarize up at the end, because this is a section where things start to go a bit out of control. Okay, so intuition tells us that complexity is a dangerous thing. We know this already as well because everybody doesn't shut up about it. The more complex your model is, the more likely it is to overfit, and that's a problem. There's a good reason for that. It's because, well, the more functions you have in your hypothesis space, the more likely you are to have one or many that fit exactly for your data. And data is noisy. So as we know, that's not a good thing. So we actually have two things going on when we're training. What we want to do is we want to get as close to our data as we possibly can that we've observed. So this is where the training and test bit happen. So we want to obtain a model that is as close as possible to our training set. But at the same time, we want it to be as close as possible to our test set. And that means pretty much what we have to do is break our empirical risk minimization principle into two different parts. And I'm going to define something called the excess risk now. And that's just a difference between what we're calling the expected risk of some hypothesis, which again is just the expectation of the risk, and the risk of the optimal hypothesis. So let's pretend, let's actually not worry about it. Let's just say that there is some F star. We don't actually need to know what it is, but in our hypothesis space, maybe if we had an infinite number of data or an infinite amount of data, we could compute some F star that is the absolute optimal F given our hypothesis set. Maybe our finite data set doesn't allow us to do that, but let's pretend that it is possible to do that. Or no, not that it's possible to do that, but in theory, one could do that if they had all the data, even though we don't. So what this looks like is just, I'm going to highlight it, two things we're familiar with already. So let's ignore the right-hand side for the moment and just say that this is the expectation of the risk of our function that we have. So the one that we've trained, which is just f hat. And this quantity here is, again, the risk of the optimal classifier, or not even necessarily classifier, whatever it is, the optimal hypothesis. So what this function will tell us is how far away the model we have is from the best possible model that we can have. Okay. Can we compute this in practice? It turns out probably not, but we can use it to analyze our model regardless. So I'm going to introduce two things, which is pretty much the same thing as introducing nothing. So on the right-hand side of this equals, we have pretty much the same thing, except what I've done is I've added this object in, and I've also taken it away. So it's just a 0. So this object in total is 0, okay? Just make sure this doesn't confuse anybody. There's no real reason to do this apart from it makes things easier to analyze. So this is a very common trick, especially in physics, where you just introduce an object that's equal to 0, because when you do that, you can make some nice analysis about it. And what this does allow us to do is to compute these two separate objects, so the estimation error and the approximation error. Okay, what are they? Well, the estimation error is cool because it pretty much just tells us how good our model Fn is in comparison to the best possible model we can have. Now, not actually, sorry, let me specify that a little bit more clear. Not the best possible model we can have, the best possible model we could have given that we specified some particular hypothesis set. So maybe we've chosen to train on a data set with a specific architecture of convolutional neural network, and we've chosen a specific space of parameters that we're going to use with it. Now, if we had an infinite amount of data or an infinite number of images to train with from our distribution, then we could get an absolute minimum risk. I mean, yeah, that's the risk. Given infinite data, we can find a function that achieves minimal risk and it is perfect classifier effectively, as long as our model is appropriately complex. That's what this object is here. So the infimum from our hypothesis set. Now, it could be that our hypothesis set is too restrictive, so maybe it's just not good enough. So, for example, you couldn't, I don't know, separate cats from dogs in an image with a linear classifier. So it's not necessarily the case that this will achieve 0 risk. It might achieve a small risk, but this might not necessarily be 0. But what we want to know is, in general, if we do a training process, so in general, if we train given the architecture we've chosen and the learning process that we've chosen, how far are we going to be away from the best we could possibly do given the constraints we put on ourselves? So we call this the estimation error.
Just one question. This F cap n is not the best hypothesis yet, right?
No, it's the best given some particular realization of the data.
Okay.
Yeah. So yeah, Fn cap is always attached to a particular data set, whereas F is not necessarily attached to any data set at all. So we have this quantity, which tells us this quantity actually is pretty much to do with the complexity of our data. And then we have a second quantity, which is the approximation error. So this one So before I talk about that one, the one on the left is what we're going to be worried about. Pretty much is going to control our generalization. The one on the right tells us how close we actually got to modeling our data, our training data exactly. So if you model our training data exactly, this term will be 0. But again, it's not necessarily the case that we actually want to exactly model our training data. That could possibly be overfitting. Okay, now I mentioned it later on, but I just want to say it now anyway. The interesting thing about these two quantities is we can't really do much about this. Okay, so there is some model. It's actually the Bayesian model that will achieve the minimum risk. Now, it's not necessarily possible that we can even compute it, but it will achieve minimum risk. And that minimum risk technically does exist, even though we don't know it. So we can never actually control this term, this group. So we can never actually really do much about the approximation here. As in, we can't really analyze it in a way that makes us comfortable because this term is just fixed. We might not know it, but it's fixed. However, this object we can control. So technically, this entire term we can control, and we can analyze that, because I guess when we're doing learning, what we want to know is, are the choices that we've made the correct ones, or are they reasonable ones? So when we're controlling our learning process, which effectively amounts to controlling this object I've highlighted here, the estimation error, we want to see how it behaves. So that's what the next section is going to be about. The super complexity regularization comes into play. Okay. So, as I said, we're not minimizing the risk, we're actually minimizing the empirical risk, which is an approximation of the risk. So, the larger our hypothesis set is, the more likely we are to find a hypothesis that can fit our observations. Yeah.
Yeah, so just in the last slide. In the first, like in the estimation error, so
Yep.
like in this case, it would be related to a bunch of parameters. So
A lot of what?
Bunch of parameters of like choice of like related to the choice of the model, like the architecture and so on. How this would be related to the because I would say, like, if I understood what we're saying good, I would say the most influenced parameter by this estimation error would be the choice of the optimizer. Because
I wouldn't say so.
okay.
The reason I would say that is because at the end of the day, you're doing gradient descent, and if you do it for long enough, you'll probably end up in the right spot. That's pretty much the gist of the no free lunch theorem. What I would say controls this most heavily, and that's what I'm going to talk about, is the hypothesis set. So remember I said that if you had a linear classifier, this term could potentially be small, or it could be massive. And if this term is small, then it's possible that this term can be small. Okay. If this term is not small because we've chosen a bad hypothesis set, then it means this term at least has to be large, and this could be even larger. And depending on how we choose that, this could be humongous. So this term completely really depends on our training set, our hypothesis set, and not on our training set or how we do training to an extent because of this. So we're taking expectation. So you have to imagine that this term is computed from a million different trainings, maybe more. And I mean, using a different optimizer isn't going to affect it that much. Yeah, you're right. It will to an extent, but it's not really that important.
Adam just forces the overfitting.
What?
Adam just forces the overfitting over the data.
Yeah, it's not that it won't affect it. It's just we shouldn't really worry about it, I think. And let's not worry about Adam for the moment because we can't analyze neural networks with this yet, or we can't analyze CNNs. So they are a bit of a problem. I'm using them as an illustrative example, but they kind of fuck up whenever we start to talk about any of this in detail.
Yeah, thanks.
No, sorry. No, I thought you were going to say something. Okay. Yes. Okay. So like I said, yeah, you have a big hypothesis set. It's very likely that you have some hypothesis in there somewhere, or at least it's more likely you have a hypothesis set or a hypothesis in there somewhere that gives us a low risk. it's more likely that you have many hypotheses that give us a low risk. So it's more likely that in general, your expected risk, which is again, this object. So it's not just the risk once, it's the expectation over many possible realizations of the risk. So it could be the expectation over the risk of 1,000 different trainings or more. The larger our hypothesis set is, the more likely it is that we have lots of them that are small. And if we can fit our observations exactly because we have such a powerful classifier, then we can overfit. And that's obviously a problem. So this is the theoretical origin of the overfitting problem. It's the complexity of the data set. So when you hear things like the VC dimension and the Rademacher complexity, this is what they were built to solve. So one way of dealing with this, and you're familiar with it to some extent, is introducing a regularization term. So when you're doing your training, you can introduce a regularization to your loss, or your risk in this case. And you penalize that risk based on the choice of your hypothesis set. So say you've chosen a linear classifier, maybe you can have a small penalty. But if you've chosen something like a convolutional neural network, you have a massively parameterized model there, and you want to penalize as much as you possibly can, because it's very likely you're going to overfit your problem. So what we do is we add this extra regularization term, C of f, which is a function of our hypothesis, because our hypothesis may be complex or not complex. So this will tell us how complex this is. Now, the actual form of C is very difficult to compute. We'll look at a simple case of that later on. But we'll just assume for now that there is some way you can compute the complexity of a function set, or not even a function set, in this case it's just a function. And we will use that to regularize our training. So in practice, we now extend our training process to this. So empirical risk minimization becomes complexity regularized empirical risk minimization. So we have this extra term in here now, and we minimize over the sum of our empirical risk and this penalty term. Okay, that can help us solve our overfitting problem. And that can help us achieve what we want to do, which is to obtain some kind of, I won't say algorithm, but we want to achieve some set of objects that allows us to get to a consistent learning process, which is the biggest concern of all. So no good if we have a model that once in 1,000 years can train to really good accuracy. We want something that is reliable and robust. That's the whole point. So I'll just explain this one more time. So we have some function, f, which is chosen from our hypothesis set, big F, given some particular realization of our data. So we have some data D with little n that this has been trained on. And we will choose a model as the optimal model if it satisfies this. That is, it is a function that minimizes this object here. So we want to find a function that not only has minimal risk, but has minimum risk also with the penalty. And sorry, I didn't really explain this, but there are certain ways of measuring the size of a data set. So say we have a finite data set. No, sorry, I keep saying data set. Say we have a finite hypothesis set. One way of measuring how large that hypothesis set is just to count the number of functions that we could possibly have. It could be large. It could be very large. Say we don't have a finite size. This becomes a little bit trickier. And we're going to work on the assumption for now that it's finite. And in practice, it actually is, even though it's so large that it may as well be infinite. But we're going to pretend for now that we're only working with finite hypothesis sets. And that sounds kind of silly, but it gets us to some nice bounds later on, some nice results. And next time I start going through this, hopefully I'll understand it better and you'll understand it better. And I'll go through a quick summary of all this again and explain how we can change this from being finite into infinite. And then we can talk about VC dimension and Rademacher complexity.
James, please, like when you're talking about the like the minimal risk and you are relating to a given loss function and so on, I'd say, do you think we are making the assumption that this loss function is covering the whole properties of our data set, while in some practical cases it couldn't? Like if you go to images or something, like it's not like always that the BC, for example, or something is covering the whole properties of our targets. So how this would be like affect the risk minimization?
My answer is actually something I thought about and I don't know the answer yet. So I'll write it down actually as something to figure out. I really don't know. I presume the answer is a lot. Yes, it will affect it a lot. But precisely why, neither of the notes I've seen, so neither of the notes, sorry, that I've used for this, or any of the notes that I've seen before this, even in the Tip Shirani book, which everybody talks about, which by the way, you've all heard of this Tip Shirani book, which is called like The Elements of Statistical Learning or something. It's a heap of shit. Don't read it. It's
That's
not.
Cool. Thank you.
It's not worth your time.
It's like everything we are making the one assumption that the loss function is robust, and the loss function is like covering 100% of properties of our data set. While if it is not measuring the like the question is if we can quantify the distance between the model output and the target, the data set target, with one loss, I mean. Like if this condition is not verified, it means we could optimize or like build the whole model on top of one property, while we'll, like this model like will be like won't get like good results in other properties.
I think it will depend upon like if it is covering the whole space or like it's looking at some local point or something. I think it depends upon the kind of learning algorithm we are using. So
Yes.
so if we are using a neural network, so our hypothesis is like each of the weights, like there could be many weights, like, and the learning algorithm which will help us to find the best G would be gradient descent. And if we are using this perceptron thing, so linear weights like W1x plus W2, so W1 W2 is a hypothesis, like is the parameter of S, and a learning algorithm would be this perceptron algorithm. So I think it depends upon the algorithm. Like I'm not sure.
It just occurred to me that actually it will be quite important. So I guess the assumption is that you have to choose it carefully. Loss will come up later on. I might forget to mention it. I'll talk about it then. When the loss comes back into it, and when I start mentioning the loss explicitly as a capital L, remind me to talk about this, and I'll see what I think of then. Sorry, I'm trying to look at you guys, so I end up looking to the side of my screen. But yeah, sorry, I just looked really weird. Anyway, so to continue, the big trouble is, first of all, that we have not the object that we want in theory. We have the object that we have in reality. We have the empirical risk, not the true risk. So the true risk is the actual performance of our model given an infinite data set, which we don't have. So we have to approximate the true risk and call it the empirical risk. But just slapping in a hypothesis set, and apparently a loss function as well, is probably not a good idea. So what we want to do is find a model that is more likely to generalize well, which is typically a model that's not going to be particularly complex. So if we find a model that achieves low risk with low complexity, well, that's great. So I don't really talk about it, but there is a method in here called, I'd actually never heard of it before this anyway. Maybe you guys have heard of it. I won't talk about it too much. It's called the method of sieves. So what that is rather than just go with a hypothesis set, so rather than just maybe go with an architecture, it's almost like a neural architecture search. Not in actual process, but in theory, not in theory, in idea. So rather than just go with a specific hypothesis set, you change your hypothesis set over time. And that may result in doing something like changing your architecture, or it may result in saying something like maybe you've chosen only to use integer weights as your first guess, and let's say binary weights, and you do your training and you find, nah, this is a bit shit. Then you update and say, I'm going to use integer weights only, which is still a restriction on all the possible weights that you can have, because typically you work with real valued weights. And you find that your integer weights, they're okay. And you try to train with your real valued weights, and you find, yeah, I get good accuracy on my training data, but as soon as I switch to real valued weights, I kind of do shit in my generalization. So you might decide that given all these choices you've made, the best hypothesis set to go with was the one that had integer weights, and you do thanks to your regularization, which tells you that you achieved minimal risk as well as generalization using your complexity regularizer, it's best to go on integer weights. You can actually use that. It's called in principle, it's something like that. It's called the method of sieves, which allows you to actually choose your hypothesis set during your training process. Although that requires assumptions before you do anything, especially about the actual structure of your data, which isn't necessarily ideal. So I'm going to talk about something that you'll do instead. And I'm going to try and hurry this up because I think actually I'm slowing down. Okay, so here's what Yasser was talking about. So yeah, you can do training, testing, and validation. That's fine, which pretty much just means rewriting the empirical risk minimization principle to look like this. So you still have your, let's keep our complexity regularizer and introduce some lambda term, which is just, it's effectively just a weighting. Let's pretend it's a weighting for now. And rather than just have our empirical risk, we have this little v, which I'm going to use to say that it means it's a valuation over the validation set and not the test or the training set or the testing set. It doesn't really matter. But we're now minimizing something slightly different. So we didn't do any training here. We just do minimization on this. So we want to choose the model that minimizes this. And here's just a specific form what that looks like. The assumption I make here is just that you have n data points, and let's just say you take the first m, call that your training set. So m for mouse. You use them for your training set, and the ones between m for mouse and n for, I don't know, nail. You use that for your validation set, and you validate on that, or testing, whatever.
There should be a minus here, right? This is in bracket, right?
Where?
N minus m minus 1, right?
N minus m minus 1?
In the denominator.
Oh yeah, I see it. I'm just sick. Nope, because I want to use my training set as 1 to m for mouse. So if I do that, then I want to take the one after as my start of my test set. So m plus 1 all the way to n. So that's where the plus 1 comes from. So n minus m plus 1. You start with m minus,
okay,
yeah.
okay.
Yeah, that confused me, which is why I had to write it down again, because when I first saw that, I was like, that's not right. Okay.
So you want to include 1m, okay.
Yeah. It's here at the bottom, n plus 1 to n.
Yeah.
Okay. This doesn't sound like it's a real thing, but it really is. So this section I'm calling probably approximately correct learning. So this is where consistency starts to happen. So what time am I on this one? Okay, we're okay. I'll try and not go the full time, so we have some sunlight left. Yes. What we want to do is, again, this is all obvious, but what I'm doing is putting a formalization on everything that we actually do on in our day-to-day lives when we're doing our work. What we're going to do is we're going to find a model or with a hypothesis space that gives us a happy medium between being very complex, so being able to represent what we want to represent, and not being too complex. So we want to find basically the correct hypothesis space. And if we can do that, then we can train effectively. And if we can train effectively, then we have some way of doing learning that gives us reliable models. So what we're going to do is we're going to establish things called epsilon delta bounds. Now, if you've done any rigorous proofs in calculus about where the notions of differentiation and integration come from, you've probably come across epsilon delta bounds. If not, don't worry, they're not that complicated. The proofs are, but in theory, they're not actually hard to understand. So what we're going to do is show with probability delta that some quantity is less than or equal to epsilon. Okay, so both epsilon and delta are going to be small positive values. So we want to show that with high probability, something is happening. Or in our case, we want to show with high probability the difference between what our model is actually achieving in terms of risk and what it can possibly achieve in terms of risk at best is low. So we want to show that in general, our model achieves a very low difference between what it did get and what it could possibly get. Or in general, our model with high probability has a low estimation error.
Is it has to do something with Hofting inequality?
That's precisely where I'm going to get to.
Okay.
Yes.
Okay.
So, yes, what complexity determines that a model is a good one? Well, it's the one for which estimation errors are small. So we can say that a hypothesis space or a function is of an appropriate complexity if we get a low estimation error. That's the thing we can control, because we can't control the approximation error, at least not as much as we'd like. So in order to actually say, again, how complex a function is, we need to introduce complexity measures. So the first one here is a complexity measure on our hypothesis space. So a large hypothesis space is likely to be very complex, but also at the same time, a complex function, funnily enough, is likely to be complex as well. So we want to have two things that tell us that. And again, we don't know what these functions look like. So this isn't actually a function, even if it's a functional. It's not even a functional, it's something else. I think it's called a functor, where you take a set as your, it doesn't matter. You take a set as your argument and you give back a real number. This basically gives a value to a set and says this value, this set of functions is complex or it's not complex, or it is high complexity or it's low complexity. So we don't really know what this function is going to look like in terms of what values are ranged between. Maybe it's between 0 and 1, which 0 being low complexity and 1 being the worst possible complexity, or maybe it's unbounded, so we have 0 complexity for a function that can't a function space that can't represent anything, and infinite complexity for function spaces that have, I don't know, infinite amount of representational power or a representative power. But that's not going to happen in our case, because if we have an infinite quantity, then we can't do anything with it. So we're actually going to prevent that from happening. Similarly, we have functions themselves can be complex. That's pretty obvious, so I'm not going to talk about that anymore. So as I said, yeah, complexity will probably increase with the dimension of the hypothesis space, because the more functions we have, the more complex it is. And it should decrease with the data we have, right? So we can train models to be less complex by choosing our model based on our data set. That's a bit nebulous, but we'll see how that works. Okay, so here's this quantity again. It's just what I was talking about earlier. It's the excess risk, the difference between what we're actually getting and what we could get. And we're interested in this quantity, which is the estimation error, which is the quantity that pretty much tells us, again, how good we could possibly do given this hypothesis space and the data that we have, and how much we generally do, or how well we generally do. Okay, so how reliable our process is. So again, we have no control over R star, so we focus on the first term. We can use the complexity of the regularizer. That'll help us find our hypothesis, and it can minimize this estimation error with high probability. So this is where the epsilon delta bounds are coming in. So we can get something, we can get a small value with high probability, which is good. So we're looking for bounds like this. We want the absolute value, or well, it doesn't have to be the absolute value, but it can be something like this. We want the absolute value of this estimation error, or something like it. Again, this is slightly different from the estimation error, but it's fairly representative of the same thing. We want it to be, or we want to show that it's exceeding a certain value with a certain probability. So typically epsilon and delta are very small. When I say very small, I mean like they're somewhere close to 0. So what this is saying is, with low probability, so some probability close to 0, the difference between how well we are doing and how well we could have done, the difference is not likely to be greater than a small value. So it's not likely to be big. So with high probability, this difference is small. That's the situation that we want. Okay, and the name of this theory comes from then a hypothesis that satisfies this kind of bound is likely to be probably approximately correct. Okay, so we can actually use this backwards, so we can go back to the start. I'll finish with this and let Taran talk now. We can actually use this to verify that empirical risk minimization is a reasonable thing to do. Even though we know it's a reasonable thing to do because we do it and it works, we can prove using this idea that it is actually the right thing to do. Okay. Taran, were you gonna, or did you put your mic on by mistake? No. Okay. Okay. So we can make this a lot easier for ourselves, or we can make it harder for ourselves. We're going to make it harder because it allows us to do something much more powerful later on, which means that we're going to assume nothing about the form of our data distribution. And anyway, usually we can't do anything about that. So, like, for example, it's very hard to assume anything about the distribution of images. You don't know what kind of distribution they're drawn from. Now, you can approximate it, sure, with a GAN, something like that. But doing something analytically, which this is all analytical, it's not going to happen. So let's just pretend that we don't know anything about our generation distribution, just that we can get data from it, and maybe that we have data from it already. And now we're going to start thinking of our loss as a sum, or our empirical risk, sorry, or our loss. You can think of this, I guess, as our loss, as a sum of random variables. Okay, so when you're doing your training, as you know, your weights are random initially, your process of going through your data is random, and your data is effectively random. So when you're doing your weight updates, every time you compute a loss, that value of the loss is effectively a random variable. Well, it is a random variable. So this risk, empirical risk, is same as we had before. But let's now call this object a random variable and just call it Li, or L subscript I. So these are random variables. And this is where what Taran was saying is the Hoeffding bound comes in, because Hoeffding bounds were things invented specifically to deal with sums of random variables. They tell us very conveniently about epsilon delta bounds for sums of random variables. Okay, and the Hoeffding bound is a particular kind of bound called the concentration inequality. And there are two really simple ones that you've probably come across before, even if you've forgotten them. I'm not going to prove them, but they're really easy to prove, and the proofs are nice if you want to do them at some point. These are the Markov inequalities and the Chebyshev inequalities. And they tell us the probability that some variable is greater than or equal to some fixed non-negative real number epsilon. So remember, epsilon is a small value, and they tell us with what probability that some variable is greater than or equal to it. Okay, sounds okay. So Markov's inequality is simple. The probability that some random variable x is greater than some value epsilon. Now this random variable can be drawn from any distribution. Oh, that's not supposed to be z. Sorry, I was changing notation when I first changed this one. This should be an x. So it's equal to the expectation of x over this value epsilon. Okay. Now, don't feel bad if you don't have an intuition for this, because I don't either. Just accept that this is true, and that's all you need to do. It can be proved in one line. This is a little bit more complicated, Chebyshev's inequality, but it's pretty much the same thing. So rather than saying that the probability that some random variable x is greater than some value that we've chosen epsilon, and this again value is small, we compute this object. So the absolute value of the difference between the expected value and the random variable itself. This all seems pointless, but if you remember, we were looking at the absolute value of the difference between the empirical risk and the expected value of the empirical risk. So actually, this thing allows us to get a very nice bound on what our empirical risk looks like. So again, I never said this at the start, but this is common notation for expected value, which I'm sure you're aware of. And this is less common, but I use it. I'm just using it for the variance. So it's just the variance of x. Okay. So using these two inequalities, which are nice in themselves, we can get a very, very loose bound on our estimation error. Okay, so this is a start. We can start to tell something about how well our learning process actually does its job. So we can say that the probability that the difference between our empirical loss given some function f minus the loss that we could possibly achieve if we knew all the data and we trained over all that data with the same hypothesis set. We're saying that the probability that that difference is greater than some small value, so the probability that it is not small, is less than or equal to this object that we can readily compute. Cool. Okay, that works really well. And
So ideally we want to minimize this term on the right-hand side, right?
Yes.
Okay.
Or we could choose this if we want later on. I'll show you how you choose that. and we could try and force this value. So sorry, you can do one of two things. You can choose this value, which changes this, or you can choose this value, which changes this.
But don't you think there is a trade-off between n and epsilon? You can say, okay, you are taking large data set n and trying to make sure this goes to 0. But the thing is, like, your epsilon could be of order of 0.1 or 0.0. It will again bring down this product to like some high, like some lower value, making this whole term goes big again.
Precisely. So in reality, when we're evaluating these objects, we can't necessarily control anything we want. So it might be the n that we already know,
Okay.
and we'll be computing the epsilon.
Mm-hmm.
Or maybe we're starting to develop some problem. We know that we have to collect some data, and we want to achieve a certain reliability with our learning process. Now, nobody's ever going to do this, but let's say we haven't collected any data yet. Well, we could say we want our model to be reliable. We want it to have, in general, this quantity having a very low value with a very high probability. So given that I want it to be very low with high probability, what is the n I need to do that? So how much data do I actually need to go and collect in order to achieve this? Now you wouldn't do it with this, because the problem with this actually is that this probability is linear convergence, which isn't good, because that means, like you said, since we have the n on the bottom here, we're going to need a hell of a lot of data to make this value small,
Yeah, because,
especially if epsilon is tiny.
yeah, because if you want to set epsilon tiny, like 0.001, then even if you take like n 1 million, then it will be, this factor will be around 1,000 or 10K. So
Yes.
it's okay, closer.
Exactly. It turns out that these bounds, as I said, are really loose. We can do way better than this,
Okay.
but not without significant amount of work, unfortunately. And that's called the Hüfting bound. So I'm going to run through this. Don't worry, again, if you don't have any intuition for this, that's fine. Just accept everything as reality, and there are proofs for all this stuff, because the proofs are horrible from everything from this point on. It's just nasty. Okay, so these are the Hüfting inequalities, and I'm just going to read them out. So this is where I changed the Z, because I didn't like Z. I probably shouldn't have kept it here either, but I did. So let's pretend that these are independent random variables. So they're drawn from some distribution randomly and independently. Okay. They are in this range. So the values that our independent random variables can take are between A subscript I and B subscript I. So maybe between 0 and 1. This seems like it might be restrictive, but it's not, because these can be anything, and it can be different for every single random variable that we're talking about. So we could have random variables drawn from different distributions, and this would still work. So again, Z1 to Zn is just a bunch of n different random variables Zi, which are drawn from some distribution, and we know that they're from some range. Now, these things we can actually know. We're going to use these two definitions just to make things easier for ourselves. So this is a sum here. So the sum of all these Zi is we're going to call Sn. This notation is a bit shit, because this is the one that they went with your man Castro's notes here, which are again generally quite nice, but they're riddled with bad notation mistakes. We're going to call Qn this object here, which is just the square difference between the upper and lower bound of the values that our independent random variables can take. And we're just going to assume that epsilon is greater than 0, right? Because if epsilon is 0, you're assuming that your model is perfect, or your training process is perfect, which means your n has to be infinite, and that's just not practicable. So we're not going to even entertain the idea that it's possible to have epsilon being 0. Okay, so again, Z are random variables. We have a bunch of them. We know what range they're in. We can sum them up and get this quantity. We can sum up their ranges and get this quantity, because the AIs might be different for each one. In practice, they never are. We have some value that we're specifying, epsilon, which we know to be small, but we're setting it as small as we want. We can say that the probability that this difference exists, so the probability that the sum of all of our random variables minus the expectation of that sum is greater than epsilon, is this quantity here. Okay, just notice that it's exponential. That's all you need to do. The probability that's less than or equal to minus epsilon, again, remember epsilon is positive and non-negative and non-zero. it's just an exponential again. With this thing on the bottom, which is important, and this thing on the top. So the epsilon goes on the top and the Qn on the bottom. I'll explain why that's important in the next slide. And the one that we're most interested in is this object. So if it returns to this absolute value of some random variable minus the expectation of that random variable. Now this random variable happens to be a sum of random variables, but it's still a random variable. And you remember that we reinterpreted our risk as a sum of random variables, as a sum of random loss values, which we got from training. So we're going to investigate the probability that our risk or our sum of random losses is lower than some bound or greater than some bound, something like that. That's the general idea here. So if the difference between what our loss actually is and what our loss could be in general, or what our loss actually is in general and what it could be at best, if that difference is low, then our model is consistent, or not even our model, our training process is consistent, and we've chosen everything well. Especially if this value happens to be low, which it can be if we choose epsilon or n appropriately. And we definitely can do that because now we don't have linear bounds, we have exponential ones. So that actually stacks up well with reality. If you've ever trained a CNN, which again I know you all have, you'll notice that the loss changes really rapidly at the start and doesn't really change at the end for a long time. Well, it does. I mean, like, it changes really slowly and it looks exponential. Well, it's probably because it is. And this is some indication that this is why it's happening. So Hoeffding's inequalities were invented long before this was a concern. These are purely probabilistic theory objects, but it turns out that they're really, really useful for us. So we're going to use them. And they tell us something about the nature of our data, that it behaves like this, that we can make these we can make these observations about what we're doing. So machine learning doesn't have to be a black magic like it is with deep learning. And someday somebody will figure this out for deep learning. Whether it's worth the effort or not is another thing. So again, the whole point of these Hoeffding inequalities is that we can achieve very tight bounds on our estimation error. So if we want, we can be very sure, very high probability, with few data, or relatively few data depending on the complexity of our model, that we're getting a very consistent process, learning process. Okay, so this is pretty much the last section. I'm going to wrap up what we have so far, because that section was a bit heavy. And then I'm going to talk about what we can do with this and where we'll go next time we start to investigate this kind of material. So first of all, the first thing we did was easy. We defined learning as a process. Cool. We did it very rigorously. So now we can say things about it rigorously. We know that the quality of the model that we get from our training process will be heavily dependent mostly on the complexity of our hypothesis space and the function itself in that hypothesis space. Okay, but also it's going to be affected by our data. So if we don't have much data to train on, then we can't do much about searching in our complex hypothesis space. So the complexity of our training process is going to be extremely high. So the more data we have, the better. We want low complexity, at least the lowest possible. Okay, so given that we can know these things, now we want to see how reliable our chosen hypothesis will be in general, given that we've made our choices about what the hypothesis space will be, what our functions will look like, what our data are. Well, maybe we haven't made a choice, maybe it's been made for us, maybe we just have the data, and we'll pretend that we've chosen clever loss functions, that kind of thing, so that Yasser doesn't get upset. So now that we can do all those things, let's estimate how reliable that process is. And we've chosen all these things, right? So that means effectively that we're looking at bounding the estimation error. We're trying to see, in general, what does the estimation error look like? Or in general, how far does the empirical risk deviate from the true risk? So what is in general the size of this difference? And with what certainty can we say that that size is within a certain region? Well, that's what the Hoeffding bounds tell us. And that's what the pack bounds tell us. The Hoeffding bound is a kind of pack bound. So we know this as a sum of random loss values, this risk value. Because we know it as a sum of random risk, random loss risk, because we know the risk as a sum of random loss values, we can do things like use the Hoeffding bounds. So we can use the Hoeffding bounds to tell us things about what in general are random variables, which happen to be not random in the sense that we're producing these on purpose by doing a training process, but we can say something about them now because they effectively act like random variables. We can now say, well, with probability delta, they will not exceed some small value epsilon, and delta is small. So with high probability, this difference will be small. Okay. And the whole point of using the Hüfting bound again is, well, instead of using the Markov bound or the Chebyshev bound, is because we want to say that we have this bound and we know it tightly. So it's very likely to be correct. And we can get tighter bounds, but again, the effort to compute even tighter bounds than the Hüfting bound is probably not worth it because this is nasty enough as it is. Okay, so let's just look at the end and how we would actually bound the empirical risk minimization process in general. And I'll show you then that we can actually compute a complexity measure under some assumptions about what our things look like. So I asked you earlier to remind me, but actually it's kind of reminded me now. The loss function is important to some extent. This is where it happens to be important. So it's not the case always that a loss function is bounded. So for example, the Wasserstein distance, the values go from 0 to infinity. Now it's a problem if we start to look at these non-bounded loss functions because we start to get infinities, which is a big problem mathematically. That I can tackle later on, so I'm not going to touch it for the moment because it makes things conceptually horrible to think about. And if we don't understand this as an idea, then we're not going to understand the maths. I'm not trying to really explain the maths, I'm trying to present it to you and show you what it means so that when you come across this, or if you want to prove it to yourselves, you have an intuition for what all these equations tend to mean. So let's pretend for the moment that we have some L. That is a loss function. It's bounded. So it's between 0 and some finite value, M. Okay, now let's not choose M because we've already used like K. It's between 0 and K. Or actually no, minus P and K. Right? It can be anything. It can take negative or positive values. Let's just say for the moment that it's finite. Okay, that's a reasonable enough thing to do because there are lots of loss functions that we use on a daily basis that are finite. And when we want to come to the non-finite ones, we discuss that at a different time. So again, we come back to our familiar quantities. So we have our random variables and our expectations. This is effectively an expectation of our random variables. Now, it doesn't look like it, but we can go and show that it is if our learning process is consistent. So using our Hüfting bounds, we can show that with a certain probability, our difference exceeds this small value epsilon. So with low probability, this object is large. And all we have to do that is to re-represent our risk as a sum of random variables, which we can do because we looked at it earlier when we wanted to look at it like that. So this factor of 1 over n is the only sticky object really here, but it doesn't really change much. It just means we have to account for that later on in our exponential. Okay, so this is pretty much what this amounts to. And if I continue, we can use this. So we can take this and use the Hüfting inequality to say something about it because this is actually in Hüfting form already. Now, let's take our loss and say something a little bit stronger about it that isn't actually any less general, it just makes the maths easier. So I said before that we're going to take the values of our loss between minus p and plus k. We can shift them to between 0 and 1 and not lose anything. It's just a rescaling. We can scale them back if we want. So any bounded loss, we can say, bounded on both sides is what I'm trying to say as well. Any bounded loss can be rescaled to the range of 0 and 1. And no difference is really made. The only thing that happens is the magnitudes of our values change, which doesn't actually affect any of the mathematics. So we're going to say that all of our loss values are in here, or that any value Li, which is again a loss value, has to be in this range somewhere. Okay. And we can always rescale it to behave like that and rescale it to behave the way it did normally as well. So we can push it to a 0-1 loss and push it back if we want to do this kind of analysis. Or we could do it directly, but it's going to make the maths horrible. So using those Hüfting bounds, so I've probably forgotten them already, but it doesn't really matter. Basically, what this gives us is with probability, that looks like this, our risk difference or our estimation error is small. Okay. So you'll notice actually that I didn't square out this term. So if I did, this n would disappear and there would just be an n on top. I didn't, just because it makes it a little bit easier to see if you're going through these slides in your own time, how I get from here to this object here. And remember I said as well that these random variables z, which are in here, they have to be between some range. So what we've done is we've specified that. We've said now they're in a range between 0 and 1. And this range is the same for each one. So this is just the difference between 1 and 0. So it's just 1 squared, and that becomes an n because we just sum n, we just sum 1 n times. So it becomes an n on the bottom. That's where that comes from. That's where that n comes from. Okay, that's a really tight bound. That's really good. That's as good as it gets, pretty much. Not as good as it gets, but you're getting there. So I'm putting the exact same equation back up here just so we have it. So again, with low probability, our estimation error is high. So with low probability, it's bad, is effectively what this equation says. So all this tells us, though, is what the risk is likely to behave. So remember, I took the expectation out here. You'll notice that that's gone. We can put it back in if we want, because we have to do it slightly different. But I took it out so it would actually fit the format of the Houghton bound. Well, I didn't do it; somebody else did. So all this equation does is tell us about one particular model from our hypothesis space. But that's, again, not what we were into doing in the first place. We wanted to see how consistent our learning process was given a hypothesis space. So this isn't good enough. We want to do this for all of the functions of our hypothesis space and say, in general, if we do training, given some random realization of our data, so we don't get to control what data we have. So in general, if we try to apply this to a different, let's say we've done CFAR, we've trained an architecture on that model and we want to train on something else. I don't know, another challenge. I'm losing them now. It doesn't matter. We want to train on something that's not CFAR. Is it likely that this model or this process of learning that we've developed is going to be good or as good as it was for the one? Well, that's what this is trying to. This is what I want to say now. So I don't want to say that this is good for one task or for one model. I want to say that this generalizes well. It's consistent. So we change this slightly. So what we want to do is take the maximum value of this for all of our f and see what's the probability that the maximum value or the worst possible estimation error is greater than this epsilon. Okay, now this is the part where my understanding breaks down a little bit, so please don't ask me questions about this. This is something I'm not familiar with. It's something called the union bound, which I've never studied stats or probability in any real detail, so I don't really understand how it works. But when you take this max over this hypothesis set, you can show this. Okay, so basically this is the same as what we had above, but now we're saying rather than just for one particular function f, we're evaluating it over the entire hypothesis space, and we want to find the maximum or the worst value of this difference, the worst value of the estimation error, and what is the probability that the worst value of the estimation is greater than some value. Hopefully that's low as well. Now it's not as low because we have this object here. Okay, so remember, if we have a very large hypothesis set, so this object represents the size of the hypothesis set, so maybe we have 10 functions to choose from. Well, this means that this 10 is introduced here, so now we are 10 times more likely to have a higher error than epsilon. Okay, that's bad, but it's not unexpected, and hopefully this value is so small to begin with that it's not something that we really need to worry about. But in practice it actually is, but we're not going to talk about that today. Okay, so hopefully that makes sense, at least intuitively. The maths, again, even I'm uncomfortable with it now, and I've been reading this for a long time, but it's actually fine when you sit down and work it out, except for this. So we've done all this. Okay, we've done all this to get the Houghton bound, which tells us what certain probability that our estimation error is relatively low, okay? But this is all to do with our complexity, okay? What we want to do is tell us straight off the bat. So let's say we've chosen a hypothesis set. We don't want to do with this analysis. We just want to say, is this a good hypothesis set to use? Well, we can if we compute some way of measuring the complexity of that hypothesis set, right? Well, we can do that now. All we have to do is take this equation here and solve it. Or well, not solve it, rearrange it a bit, and we can find a functional form for a complexity measure. Now, it's not the best one, but it's one that will suffice for now. So remember we had earlier that function C of f, which was a complexity measure of big F being our hypothesis space, and C of little f being the complexity of our particular model. We can show that the difference, or well, we've changed it slightly. So remember now, this also takes a little bit of mathematical trickery, but we've gone with not the absolute value, we've gone with just the plain difference between them. We can show that the estimated the empirical risk of a particular function f is less than or equal to the minimum risk that we can possibly achieve with our hypothesis set that we've chosen, plus some complexity measure here. So this allows us to measure the complexity of, in some way, of our data set. Or not our data set, I keep saying it. It allows us to measure the complexity of our hypothesis set. Okay. Now you'll notice that we've actually put the delta term in here. So actually what I did to get this, well, I didn't do it, but I verified it actually does work. Remember I said earlier that we have these epsilon delta proofs. So effectively what we wanted to do was show that this object is greater than or equal to epsilon with probability delta. Well, let's just assume that this is delta. Then we rearrange it and try and solve it for epsilon. We can get this term out, which is effectively what happens. And yeah, now we can actually compute the complexity, given that we've chosen to have a low or a high probability, have high error with low probability. So this also depends to some extent on delta. Now, this isn't actually necessarily desirable either. This actually depends on something that we've chosen, but it's a start. Okay. So this is the last slide, and I'm just going to say some things about this before I finish up. So again, this is the exact same thing we had in the other slide, but there's some important things we need to know about it as well. First of all, as we decided from the start, it's completely independent of the distribution that generated our data. That's good, because, well, I mean, we don't know anything about it. So if we wanted to compute this without knowing anything about it, then it's a good thing that we don't include it. And it would make sense intuitively that we should include it because, well, I mean, the distribution that generates our data surely has something to do with the complexity of the function that's needed to represent it well. But in theory, we don't need that. That's interesting. It depends only on the hypothesis set we've chosen. The actual quantity of data that we do have, which is the n, and our delta. So we can bound our error with these objects that we know or that we can choose. So everything we have, everything that we want now, in a sense, we can achieve. It might not be the best way of doing it. It might not be the most effective way of doing it, but we can do it as a start. Interestingly, the complexity now is exponential in the size of the data set and in the hypothesis set. Again, it's what we said earlier, and it's what we expected. So we notice this when we're training anything, when we're training a neural network, that the loss tends to decay exponentially. If it doesn't, there's usually a good reason for it not happening. But also, this term is the most problematic of them all. And this is why we know that the work isn't done. It's because, first of all, f we've assumed to be finite. That's a big assumption. It's not finite in most cases. Or sorry, the size of f, of curly f. It's just not finite. So let's say that we want to say with probability, let's say we want to say with high probability that our estimation error is low, or effectively that the difference between these two objects is low. Well, what happens when our hypothesis set is infinite? Well, this term explodes Wait a minute. Yes, these terms explode. That's not good. So we have to have, wait a minute. No, I fucked something up there. No, it does explode. This term explodes, which means we can't actually estimate. We can't estimate complexity then, right? So if we can't estimate the complexity of a hypothesis set that's infinite, which is typically the kind of hypothesis that we work with, then this complexity measure is useless to us. So this isn't where the story ends. What we need to do now is come up with something that allows us to measure the complexity of infinitely large hypothesis sets. And it makes sense that we should be able to do that, because in an infinitely large hypothesis set, right, a lot of them are going to be the same, or at least they're going to achieve very similar risk values. A lot of them are going to have very high risk values, sure, but some of them are going to have low risk values. So it makes sense that we, at least in theory, should be able to compute the complexity of an infinitely large hypothesis set, such as the set of parameters that we could technically use for a convolutional neural network with many parameters. Even for, like, in practice, actually, a linear model has an infinite number of parameters, right? So if we wanted to measure an infinite possible set of parameters that I could use. So even if we actually really wanted to compute the complexity of that in practice, we kind of couldn't. That would be a problem. But because we're assuming, in some sense, justifiably, that we don't necessarily work with an infinite number of possible hypotheses, this kind of works, but we need to go further with it. So that is where the VC dimension comes in, and that's where the Rademacher complexity comes in. They solve these problems for us. And then we'll be able to more rigorously look at the consistency of the learning process. But for now, we actually can talk about consistency of learning processes. Even though it's a painful process, it's possible to do it now. Okay, that's it.